Hey, welcome back to the lecture. This is lecture 5. And last time we were looking at the division algorithm and we proved it as a theorem, but perhaps a few comments would be in order as to why this can be called an algorithm. And to understand that, you will have to look at the proof since it contains the steps that you would have to follow in an algorithm fashion to find the answer to the question, what is the quotient and what is the remainder? Namely, you subtract the candidate for a quotient iteratively until you find a number that is small enough so that this quest becomes trivial, as would be the case of case number 2. Now, we won't really treat this as an algorithm because it isn't interesting enough yet. But hopefully, if we have time, I will cover another algorithm today whose statement as a theorem is way more evident, but the steps itself, when you want to see it in an algorithmic fashion, are way more interesting. And it is something that you're expected to know, if not by hand, then at least know that you should be able to code this if the opportunity arises. And if I have time, I will share my console with you and tell you how you can program this. Okay, so I think that answers the first question that you can see at the top of the screen. Why is the division algorithm called an algorithm? Okay, a very elementary definition is that if you're given two integers a and b, we say that a divides b, or a is a divisor of b, or b is a factor of a. If you can find a third integer c, whose product with the small one gives you the larger one. And this isn't that different from the definition that I gave of the partial ordering that is bestowed upon the natural numbers, in which you're basically changing the same definition, just use a product instead of a sum. Now, that order is very familiar to all of you, I presume, and I mentioned it's a linear order because it satisfies trichotomy law. In other words, you can picture this as being points on a line. Left means small, right means large, or whatever. This is obviously completely arbitrary. What I want to convince you of is that the relation that I just defined, by the way, if this situation arises, we will use the notation A, vertical bar, and then B, right? So this is a relation between two numbers, between integers, and I want to convince you that this is a type of order as well. It won't be as nice as a line, but it will tell us crucial information as to how the integers are constructed. Not in the abstract construction that I gave earlier, but rather in a more essential way. Let me give you some examples of the definition that I just wrote down so that we're all on the same page. Let's see, 2 divides 4, because 2 times something is 4. And that something is 2, which highlights the fact that these integers don't need to be different, right? For any integer z, z divides itself. Any number divides itself because 1 times, actually I should rewrite this the other way, because z times something, namely 1, is z. This also tells you, by the way, that 1 divides z, right? So every number divides itself, 1 divides every number. Let's write down some more properties. If 0 divides a number a, there's no part of the definition that excludes 0 from being taken into consideration. So 0 being written on any side of the relation is a valid question. So what do you think happens if the integer 0 divides some integer? Maybe I should use the same letter, z. What can you conclude about this? That is the first question. And by the way, I would like to point out that I will give you examples of showing that things divide other things, but showing that something does not divide something is slightly more complicated. Okay, so I got some replies in the chat. I think this might be more interesting than I thought. So question is does 0 divide 0? Does 0 divide anything? But particularly does 0 divide 0, right? Now there is something that we can, of course, conclude. If I take any integer z and I multiply it times 0, I get 0, right? That is a rule that we did not prove, but it follows in a very straightforward way from the axioms that were introduced. This is true for the natural numbers too, obviously. And what does this mean? It means that z divides 0, right? So any number divides 0. In particular, 0 does 2. So the answer is yes. Now, if a number is divisible by 0, then that becomes a little trickier, right? What do you think we can conclude from this situation? That you can certainly find numbers that don't divide 0, or sorry, that are not divisible by 0, right? For example, the number 4 is not divisible by 0, because if you try to multiply anything times 4, sorry, anything times 0, you will never get 4, right? You always get 0. So I claim that this implies that z must be 0. The only number divisible by 0 is 0 itself. But the important takeaway here is that 0 is divisible by 0. Okay, I think that was enough examples. Attend the tutorial and you'll find more interesting examples and elementary properties of divisibility. As always, solutions will be posted after the tutorials are over. Okay, so what can we say? Maybe let me write it like this. The lattice. If you take the integers and you sort them with this new relation that I just defined, then what do we get? Now, just to keep things simple, of course, negative numbers can divide positive ones and the other way around. But right now, let me just worry about non-negative numbers. So let's just do this for the natural numbers. The reason is that the integers are kind of weird, right? In the integers, you don't have anti-symmetry. Maybe I should mention that before. Just 1 second. There you go. Okay, so another property is that if a, b are natural numbers as opposed to just integers, and they divide each other, each one is a divisor of the other, and of course they must be the same number, right? This is anti-symmetry as previously defined. So the question is, what if a, b are just integers? Can you still conclude this, that if they divide each other, they're equal? And the answer is no, right? So -2 divides 2, and 2 divides -2. For one, you use the number -1, and for the other one, well, the same thing, right? -2 times -1 is 2. Therefore, -2 divides 2. Now, 2 times -1 is -2 as well. Therefore, 2 divides -2. So a number and its negative always divide each other, even though they are not the same, right? So keep this in mind. There's no anti-symmetry in this more general relation, which is why I want to just worry about the non-negative numbers for now. So here's how we do this. You need to recall that we've already mentioned an important lattice structure. So recall that if you take the power set of any non-empty set and you order it with this relation, that relation is also not linear. In fact, they have a lot of things in common, right? Every set is a subset of itself. You have transitivity. That same thing happens with divisibility, right? So there's a lot thing going on here. There's a lot of common properties to these two relations. So recall how this is sorted. You have X, which is the superset of all these elements. You have the empty set down here, and you have a bunch of stuff, right? You have singletons as a first layer, and then you have a bunch of stuff here, and this forms this weird structure. Now, what does divisibility look like? Well, I just convinced you that everything divides 0, and I also hopefully convinced you that 1 divides everything. So in this order, 1 has to be at the bottom, because 1 is to the left of every integer with this order. So 1 is indeed the smallest element, and 0 is the largest. Now, what could you tell me about other integers? We have covered 0, 1. What about the number 2? Well, 2 has to be somewhere above 1 because it is divisible, and it has to be below 0 because it is a divisor. Now, the number 3 tells you something interesting about this. It tells you that this is not a line, right? Number 3 cannot be compared with the number 2 because 2 does not divide 3, and certainly 3 does not divide 2. So you cannot compare these two elements with the order. There's no reason to put one above the other one, right? They don't compare. They're not related in any way. What about the number 4? Number 4 is the next integer in consideration. This one is divisible by 2, but not by 3. So again, you get a very similar lattice structure to the one that you get of the power set. And there's a question in the extended problem set that asks if these two lattices could ever be the same, could ever be equivalent or isomorphic, right? Isomorphic would mean that you can relabel the elements so that you get the same thing, right? You relabel every set into a natural number and in reverse, and you should get the same lattice. Now, the spoiler alert is that the answer is no. This is never possible, but I will let you figure out why this is not possible. The next number in consideration would be 5, which is not divisible by anything except 1. Next number, you can write maybe number 7 here, and this goes on forever, right? And I think you already see the pattern, right? Prime numbers play the same role that singletons played in the other lattice, right? So this is the natural numbers ordered by divisibility. And the bottom layer that is not trivial, that is not the minimum element, are called the minimal elements, right? So there's a distinction between minimal and minimum. In a linear order, these are the same thing, but here they're not, right? Minimal means there's nothing below it. So these elements, the singletons, for example, if you remove the empty set, would be the minimal elements. And what would be the minimal elements of the divisibility lattice? Well, that's prime numbers, right? Things that are not divisible by anything other than the trivial divisors, which is 1 in itself. I skipped number 6, but of course you can tell number 6 is a join. It joins 2 and 3, right? Now you remember that we had this zoom in situation where if you have two sets A and B, they will always join at the top. There's a smallest upper bound, which is the union, right? And there's also a greatest lower bound, which is the intersection. So zooming in, you had this weird situation that looks like, what's this, a rhombus? I don't know about geometry. Okay. What is the analog situation for the natural numbers? Consider the numbers 3 and, let me think about this, 4. Every pair of numbers has a lower bound, which is 1, because 1 is a minimum. 1 is the lower bound of everything, so it is below every pair of numbers. Similarly, every pair of numbers is below the number 0. But the question is, do these paths meet earlier, sooner, if you start walking out from these two numbers? What would be the equivalent of the lowest greater bound and the greatest lower bound? I'll give you a few minutes in the chat to answer this question, and then I will define this symbol. Any ideas? Okay. 3 times 4 for the upper bound. Yes, that is correct. So the upper bound would be 12, which is the product. Now, let me change the example a little bit to make it less trivial, right? So instead of 3, let me write 6. The answer is still 12, right? The answer hasn't changed, but now I change the question, and it is no longer 4 times 6. That is 24, which is too big, right? That's not the first time that they meet. You start walking upwards. So what can you say about the lower one? What is the number, the integer, the greatest integer that divides both 4 and 6? Of course, I could define this for many integers, not just 2. A lot of people only define this for positive integers. I don't think we really care about that. Is the biggest, the largest natural? Examples. So the first example, as some of you pointed out in the chat, is that this is called the least common multiple. Why is it called that? Well, it should be obvious from the way I wrote down this lattice, right? And this is the greatest common divisor. So these play the role of union and intersection in this weird universe of divisibility. Does someone have a question? Okay. So an example is that the greatest common divisor between 4 and 6 is 2. 2 divides 4, 2 divides 6, both are even numbers, but you cannot find any number bigger that would still mutually divide those two numbers. Another example would be GCD. What about something more sophisticated like 56, I don't know, and 15? What can you say about the GCD between these two? What is the greatest common divisor between an integer and 0? Everything divides 0, right? What do you think this should be? And then we can prove the first non-trivial property about the greatest common divisor. Let's add a name. So the theorem I want to prove to you is called the Euclidean, or the extended Euclidean algorithm. And here it will again not be maybe evident why this is an algorithm, but I will actually have to show you why this is an algorithm. And maybe I can even tell you how you could code this. So it only takes a few lines. So the algorithm says that just worry about natural numbers for now. The greatest common divisor, or let me rewrite this, sorry. For a natural number and d bigger than 1, we cannot divide by 0, right? We cannot divide using the division algorithm, we cannot divide by 0. If the quotient remainder formula gives a equals dq plus r, quotient being q, remainder being r. So what we do is we have two numbers, a and d, and we want to find the greatest common divisor between a and d. What the algorithm says is that the greatest common divisor between a and d, which are the numbers we started with, the ones that are being asked as part of the question, is the same as the greatest common divisor between d and r. Notice that the quotient plays no role because, yeah, we don't really care about the quotient most of the time, right? Now, who can tell me why this is an algorithm? I'm just stating a fact, right? I'm just stating an equality between two numbers that I just defined, the greatest common divisor. Why would the fact that two greatest common divisors are equal give you an algorithm? Let's maybe skip the proof for now. We can do the proof later. Or do you want to do the proof now? Who can tell me why this is an algorithm? Okay, so Bill wrote in the chat that the keyword, of course, is recursion, right? If you're interested in computer science, then you might have heard about the concept of recursion. That is the one word that tells you exactly why this is why this is possible and why this is an algorithm, right? So indeed, when you apply the quotient remainder formula or the division algorithm, which is already an algorithm in itself, two things happen. You find a remainder, quotient we don't care, but the remainder is always smaller than d, the number you're dividing by. And that tells you why this recursion will work, right? Because if r is smaller than d, and d is typically not bigger than a, right? It's this thing we're dividing. That means that the numbers on the right are always smaller than the numbers on the left. So if you do this multiple times over and over again, eventually the numbers shrink until they become trivial. And trivial is the example number 3 that I wrote at the top, right? Eventually, if the numbers become small enough, eventually the remainder has to be 0, right? This needs to happen because that's the reason why recursion works abstractly, right? If you want to look at this in a more set theoretic way, you should look up the well-ordering principle, which we didn't really mention, but it's the reason induction works. The reason strong induction works in the natural numbers is because of this property, right? You cannot find infinitely strictly descending chains. And that's the same reason why recursion works. So the biggest takeaway of this class should be that learning how to do proofs by induction is the same thing as learning how to write code by recursion. So maybe let's do a few examples before. So who can tell me what the answer is to example number 3? What is the greatest common divisor between a and 0? Everything divides 0. So any number is a candidate to being the GCD of anything in 0, right? Who can tell me the answer? Okay, so let's do the proof later. Proof is not really that important right now because the proof is not by induction, right? So this is just a property, an equality between two numbers. So why is this an algorithm? How to use this? How to use this algorithm? So given that you did not provide me with an answer for example number 2, because either you're asleep or you haven't figured it out, I will answer this by applying the algorithm and solving this for you. Yeah. So how do we use this? Let's say that you want to compute the greatest common divisor between the numbers 56 and 15. Now, according to the algorithm that I just described to you, this should be the same as finding the greatest common divisor between d, which here is played being, the role of that is being played by the number 15, right? So maybe I should write it down. Greatest common divisor, 15. Now, what is the remainder? Well, for that, we have to apply the other algorithm, right? The division algorithm, which we don't really think of as an algorithm because we can usually do this in our head or with a calculator. So 56 divided by 15. Maybe I should write that down. Now, an important question, by the way, is what happens? What happens if you start with a small number, right? If we try to compute the GCD of the same numbers in reverse order, should be the same thing, right? The greatest common divisor is the element of a set, and the elements of a set, the order doesn't matter. So this should give us the same answer. But if you plug this into the algorithm, it does not give you the same steps, which is interesting. And I will let you figure out why. And I will also let you figure out why the algorithm doesn't care and it will give you the same answer, even if it requires more steps. Okay, so 56 divided by 15. 15 multiplied times 4 is 45. And multiplied times 5 is 75. Does that even make sense? Sorry, multiply times 4 is 60, right? Okay, so multiply times 3 is 45. If we go over, then it's too much. Now, what is the remainder? 45, shouldn't that be like 11 or something? So the remainder is what we plug in. Now, as promised, the numbers shrink, right? The numbers to the right, 15 and 11, are smaller. So if I do this over and over again, eventually I will have to hit the bottom. The bottom is 0. Okay, so 11 times 1 is smaller than 15. 11 times 2 is already bigger, right? So the remainder is 4. Quotient, we don't really keep track of that, but whatever. Remainder is 4. So now I'm not going to rewrite the whole thing, but if we keep doing this, dividing 11 by 4, we get 2, right? Because 3 is already 12, which is bigger. Remainder 3. And 4 divided by 3 is 1 plus remainder 1. And finally, 3 divided by 1 is 1 times 3, and the remainder is 0. As promised, this always happens. You always have to reach the bottom, because otherwise you're contradicting the well-ordering principle, right? Does this make sense? You can also prove this by strong induction. But anyway, so here's the magic. The last step before you hit the bottom, the last step, that remainder is always going to be the greatest common divisor. This is always the GCD. But there is something else that this algorithm tells you that you might not be able to figure out that easily, right? Maybe you figured out that 56 and 15 have a greatest common divisor of 1 without having to apply this algorithm, maybe by splitting them, factoring them into primes or something like that. But there's something that I bet you would struggle with if I didn't tell you how to do this in this mechanical way. This takes a little bit more effort. What if we do the same algorithm, but not apply it in reverse order? Why would we want to do that? You'll see in a second. Okay, so here I'm writing up to down. Now I'm writing, down to up. So we're going to take the remainder, the last remainder that is non-trivial, which is 1, and we're going to write it as a linear combination of the two numbers that came before it, namely 4 and 3. So we can always do this because it's just a matter of solving to one side, right? So this would be 4 plus -1, 3. Now, there's no simplification needed here, but what if we do this over and over again? The next remainder is 3, and 3 can be written in terms of 11 and 4, because 4 is the number that we divided by, and 11 is the number that we divided. Now, if I do this, you'll notice something funny. What if I write 1 as 4, and just substitute in this copy of 3 for the last two numbers? Because this is the remainder, right? 3 is the previous remainder that I got. So this should be -2 times 4. Now, everything I've written so far is written in terms of only the numbers 4 and 11, which is the stage that I'm at. So maybe I should simplify this a little bit. How many copies of 4 do I have? Do I have 1 plus -1 times -2? That should be 3. I'm not great at arithmetic, so please correct me if I'm wrong. And -1, 11. It still adds up, right? Because this is 12 minus 11. Okay. So for the last step, I have to plug in the number 4. Sorry, this isn't the last step yet, but okay. The number 4 is the last remainder that we got, which is 15 plus -1 times 11, and then something times 11. And you'll notice, actually, I'm not writing this very nicely. Let me change this 11 to the right side. So that makes more sense. Now everything is written in terms of 11 and 15. So let us simplify. So how many copies of 15? Did I miss a 3 here somewhere? That one, right? So I have 15 times 3 plus -3 plus -1 is -4. Now, can someone please verify if this still makes sense? I have -44 and 45. Okay, they still add up. What was it? -4? Okay, so if I plug this in reverse order until I get to the top, let's just do this. So 1, here the remainder is 11, so I substitute in all copies of 11. What is 11? 56 plus -3 times 15. I should have picked a simpler example anyway. -4, right? And now we simplify and we get 15. 15 times what? Oh boy. 3 times -3 times -4, which is 12. 3 times 12 plus 12, sorry, would be 15. And how many copies of 56 do I have? That should just be -4. Now, you can verify if that's correct. Hopefully it is. The point is that the numbers that I started with, namely 56 and 15, are here, right? And the number 1, which is their greatest common divisor, is being written as a linear combination of those two numbers. Now, of course, you might need negative integers, negative coefficients, as I do here, since both of them are positive. That is to be expected. This is not unique. The algorithm will give you a unique answer, but this is not the only answer to this question, right? It's not necessarily the only way to write those two numbers as a combination. So keep that in mind. The algorithm will always give you the same thing. I mean, there's no choice here, right? There's no point at which we have to take a choice, make a choice, except maybe for the order. But this is not the only solution. Okay, so the takeaway is, the conclusion of this is that this algorithm can be used for two things. Okay, so someone's asking, this is not the only answer. If I ask you, can you write 1 as a linear combination of 15 and 56? Then no, this is not the only way. And there's a way for you to produce all possible answers if you have 1. So typically you will find infinitely many pairs of coefficients that satisfy this. My only point is that the algorithm will only give you 1. It will only provide you with 1. Because there's, like I said, there's no choice, right? There's only one way to do this. Yes, you're welcome. Okay, so the takeaway is GCD of two numbers is a linear combination of A and B. Now, the general statement that makes this true is known as Bezout's identity, which was discovered thousands or hundreds of years after this algorithm. But there is a difference between these two statements that is very subtle, which will allow us to shortcut most of number theory if we do that properly, which is the goal of the next class. And yes, okay, that's a great question. So the same thing that I just did now, you have to do as part of the quiz that I wrote a few minutes ago. And I think I just picked different integers. They should be fewer steps if I pick them the correct way. But yes, please, you can write them in the same format. It's not really that important. I find this easier to keep track of, making two columns, one left, one right. And maybe in the meantime, I can share my console with you, tell you how you would code this if you're into that sort of thing. But in the meantime, let me know if you have any questions, and I will give you a few minutes while I set this up to maybe solve the quiz and submit it. If you have any questions or you get stuck, let me know. But it's the same procedure, it's the same algorithm that I just described to you. This algorithm is not being covered in the second problem set, but it is a perfect candidate for a question for the final exam. Because this algorithm is not only used to find the GCD, it will be used to invert modular congruences, right? And that is very important because it tells you how to solve pretty much every linear, even systems of linear congruences. So this algorithm is very important, even though it's not directly being covered yet by the problem set. So keep this in mind. And for the quiz, yeah, for the quiz, it's fine if you just write the final answer, but make sure that you answer both questions, finding the greatest common divisor and finding the coefficients that make it into a linear combination. Okay, so in the meantime, let me just show you my console. This is mostly for those interested in computer science. This is slightly out of the scope of this course, but I don't know, I like this sort of stuff. Let me see if I can make this work. So I'm sharing my console and I just open up a Python terminal. So maybe I can type in definition GCD of two integers a and b. And okay, I think I have to indent inside the console too. Okay, so if one of the numbers, namely the one on the left, is already 0, then I have to return a, because the greatest common divisor between any number and 0 is just the number, right? Given that 0 plays no role, it adds no information to the GCD because everything divides 0. Okay, now hopefully this works. Okay, now in the other case, what I have to do is I have to divide A by B and then apply the algorithm recursively, right? So let's see if I can make this work. How do we divide A by... You return the GCD of the numbers B and the remainder, right? The remainder, if I'm not mistaken, should be A, parentheses, sorry, not parentheses, A, what do you call that symbol? Percentage, B. And this should work. Doesn't work, then I don't know. GCD between 56 and 15 is 1. There we go. Isn't it like magic? It's four sentences in Python, and it's already a recursive algorithm that correctly find the GCD. Now, if I wanted to find the coefficients, it would probably take a little bit more of work. Okay. So the numbers, I forget what the numbers are, the ones I gave you in the quiz. Can anyone share that with me? What numbers did I put in the quiz so we can verify, and maybe that can help you out if you want to know. 26 and 8, thank you. Thank you, thank you. 26, sorry, 27 and 8. Okay, so these are also co-prime, right? The GCD is also 1. Now I could have modified the definition of the function so that it spits out whatever step it's at. Maybe that would have been useful. But I think I would have to retype the whole thing, right? Okay, yeah. So coding in the console directly isn't ideal because of this indentation thing. But maybe I can add like a print statement or something. Anyway, you can mess around with this in your own time, but I just proved to you that the algorithm works, and this is actually doing recursion. If I pick two really big numbers, then this will take a long time, right? This will branch out like a big tree. Anyway. Okay, so any questions about anything I've covered so far? This algorithm is quite important. Like I said, right now it might not seem that way, but once we are inverting modular congruences and stuff like that, this algorithm will become crucial for finding inverses, solving things. Yeah, every time your computer encrypts something, it's doing this algorithm several times. If you've ever heard of the RSA encryption algorithm, this is a crucial step. At the beginning, I said that 0 divides 0, but from the concept of division that we know, shouldn't 0 divided by 0 be undefined? Okay, that's a good question. And sorry, I'm not showing my screen anymore. So there's two things happening here. There's an operation of division when you take a number and you divide it by another. That operation does not allow for 0 to be the thing you're dividing by. And if you want to know why, if you try to code that algorithm and you apply it, then it will never stop. It will never halt if you try to divide by 0. Now, the concept I'm defining here is not an operation, it's a relation, right? So I'm claiming a fact between two numbers, that they are related in some way. And with this relation, there's no reason to exclude 0. 0 is in fact related to everything on the right side. Everything divides 0, right? And the only thing that divides 0, well, that would be 0. But in particular, 0 is an integer that divides itself, like any other integer. Yes, you're welcome. I didn't answer this question right here, but I already did it as part of the algorithm. So the greatest common divisor between any number and 0 is, of course, the number, because 0 adds no information to this. And this is why you know that this algorithm will always halt in a finite number of steps, because eventually the remainder has to be 0. Okay, I think that's everything that I want to cover for now. I don't want to cram in a whole proof into the last 10 minutes, so I'll stop the recording